will keep working together with MSA.
Yeah.
So I'm very happy.
We will keep bothering you.
Please, I really, I will keep engaging with you and then Sue and then this webinar with MSA. So it's basically I have the same research topic and the membrane and the water and they're all very much connected. So your topic is one of my major research area, MBR spider. Very much interesting. So we will see what collaboration we can do in the future.
Sure.
Yes.
Okay, it's almost time. I will let all the participants to join now.
Yeah.
Okay. So Felicia, later on, it's passed to you. You can start anytime. Okay, and I will start to record at that time. Okay.
Good luck, Faida.
Shall we start now?
Recording in progress.
Hello everyone and welcome to the webinar. I'm Felicia from University of Auckland. It's my pleasure to chair today's webinar. This webinar is co-organized by ARC Energy Efficient Separation Research Hub at Monash University, Monash Center for Membrane Innovation, and the Membrane Society of Australasia. The speakers for today's webinar is Professor Faisal Hai. Professor Hai is the Director of the Strategic Water Infrastructure Laboratory at the University of Wollongong, Australia, and one of the Director of the Membrane Society of Australasia. He is the lead editor of the book Membrane Biological Reactors, which has been among the top 5% bestseller from the IAA Publishing UK. In this talk, Professor Hai will share his experience in working with the inventor of the MBR technology, Professor Kazuo Yamamoto at the University of Tokyo, and how this has shaped his research career. The talk then introduces the latest development in the field from Professor Hai's group. Before we start, please remember to keep your microphone on mute, and if you have any question, you can post your question in chat. Please join me to welcome Professor Faisal Hai. Faisal, I pass it to you.
Thank you, Dr. Felicia, for your kind introduction. I would like to thank the organizers for inviting me today. As Felicia has explained, today I'm going to share with you some
Sorry, Faisal, to interrupt you, your screen is not in full.
Is it okay to do now?
Yeah, now it's good.
Thank you. So today I would like to share with you some snapshots of my research journey in the field of membrane bioreactors. Now this slide is for the early career researchers in the audience, just so that they can have a bit of idea about one of the pathways to an academic career. Clearly this is just one of many pathways, but the main thing that to extract from this slide in the context of today's presentation is that I started to learn about membrane bioreactor from my master's, which I was conducting at the University of Tokyo. And since then, it has stuck with me as one of the main topics of research. So we all know that in membrane bioreactor, we achieve the separation of the biological sludge from the treated effluent by membrane filtration. This is different from using the settling tank, which relies on gravity settling and therefore is problematic and inefficient. Now, the current format of MBR, where the membrane is submerged into the bioreactor, was proposed by Professor Yamamoto at the University of Tokyo, who happens to be my master's and PhD supervisor and my mentor. Now, because of the compactness, because of the replacement of the settling tank by membrane separation, MBR plants can have smaller footprint. And in some examples, we have seen that the new plant size can be almost half of the original conventional biological treatment plant size. Now, because of that compactness, you can expect to find MBR anywhere, be it cruise ship or be it a small community wastewater plant, which can blend well within the surrounding environment or the surrounding structures, therefore avoiding the negative public perception about having wastewater treatment plants in their backyard. Now, clearly, compactness is not the only advantage that MBR provides us. Because of the membrane separation, we can have suspended solids-free effluent, which can sometimes help us in having effective disinfection and so on. I assume that the audience is aware of the advantages of membrane bioreactor. Now, the work that I did during my tenure at the University of Tokyo involved development of membrane bioreactor, which can achieve better biodegradation of recalcitrant compounds. In this case, I worked on dyes, textile dyes of many different chemical structures. And we showed the technical feasibility of using some fungi with special degrading capacity of recalcitrant compounds, which would not be biodegraded by normal bacterial culture that you can find in conventional biological treatment plants. We do not have the time to go into the details of the basic principle in how these fungi works and so on, but you can refer to the publication that's shown here. Now, MBRs have membranes, and membranes get fouled. Like many of you, in my research too, I found that controlling the fouling of membrane, particularly when you are trying to treat high-strength industrial wastewater, which contains sticky chemicals, it is challenging. And I spent many sleepless nights to think about what am I going to try next to prevent fouling of the membrane in my MBR. After trying many different module designs and doing many membrane autopsies, trying different regimes of chemical cleaning, and trying different methods of aeration enhanced membrane fouling mitigation, we were eventually able to find a combination that showed good performance. Now, it is very challenging to show my work at the University of Tokyo by just 2 slides, but we do not have much time, so we'll just have to move on. So after spending 7.5 years at the University of Tokyo, I achieved a lot. Yes, I got a PhD. I got some publications, but I think the major focus was I developed my passion of MBR research there. And above all, I found a mentor, a lifelong mentor in Professor Yamamoto. So it was time to move on. I came to University of Wollongong. So what have we been doing at UOW? So at the Strategic Water Infrastructure Laboratory, we conduct research on different aspects of membrane bioreactor, starting from the membrane type and formats, through to water reuse risk assessment, and up to management of sludge or recovery of nutrient from sludge, and so on. Our major focus has been on the removal of emerging contaminants, for example, the antibiotics and antibiotic-resistant bacteria and gene, microplastics, PFAS, or endocrine disrupting compounds. So today's presentation is going to focus on removal of emerging contaminants by MBR. In this connection, I wanted to mention that membrane bioreactor is the core. However, we have, over the years, we have tried to formulate hybrid processes, having membrane bioreactor as the core, so that we could derive synergistic performance by these combinations. So in some of the slides that I'm going to show, this will be evident, but we do have other work that shows that work. Right, so membrane bioreactor for emerging trace organic contaminants removal. In this study, we conducted a mass balance of the emerging contaminants. How much is being removed, how much is escaping from the bioreactor with the treated effluent, how much is getting absorbed onto sludge, and so on. So as you can see from this graph, many compounds can actually get biodegraded. However, some of them are resistant to biodegradation, and therefore they will remain in sludge. Whereas some of the compounds who do not have significant absorption onto sludge, they will escape with the permeate, that is the treated effluent. So based on this work, we proposed a framework of trace organic contaminant removal by MBR, and it was demonstrated that some of the contaminants will still have low removal by a conventional membrane bioreactor. So we have to think about the approaches to improve the performance of chalk or trace organic contaminant removal by MBR. There are a few approaches that we explored. One approach was to improve the biodegradation by introducing microorganisms of spatial degrading capacity, or to try integrated processes, for example, combining MBR and powdered activated carbon in the same bioreactor, or combining advanced oxidation process with MBR. And of course, that we also tested post-treatments. So what happens if we use a granular activated carbon column after MBR, or high retention membranes after MBR treatment? Or could we couple high retention MBRs within the main MBR rather than as a post-treatment? So these are the few approaches we explored. Now this study showed the performance of post-treatment, so nanofiltration post-treatment. Clearly, it shows that the compounds that were not well removed by the MBR could be, that their removal could be completed by using a nanofiltration post-treatment. In this connection, we also tried advanced UV, ultraviolet photolysis as a post-treatment. Again, like nanofiltration post-treatment, by UV post-treatment, we were able to complete the removal of certain compounds that would not be removed well by conventional MBR. However, we also noticed some very interesting example of synergistic effect of these, of combining them. For example, the graph on the right here, we show the removal of carbamazepine by UV photolysis. But when we fed this UV reactor by the wastewater that was pre-treated by MBR, we found that the carbamazepine removal was much better. So it means that we are having a synergistic impact when we combine two different kinds of biodegradation. Sorry, two different kinds of degradation. Right. We subsequently tried combining activated carbon absorption with MBR. One option was to use it as a post-treatment, or directly dose the powdered activated carbon into the bioreactor. And we showed how resilient the activated carbon absorption can be if we combine with MBR. In this graph, we compared the stability of the activated carbon absorption if we use it as a post-treatment compared to if we directly dose into the bioreactor. And we found that actually activated carbon can work better if we directly dose them into the bioreactor. So in terms of treated volume per unit weight of activated carbon, the second option showed better performance. So that indicated that when we added an adsorption process, the biodegradation was actually improved. And that was very interesting, that combining two processes, we are enhancing the biodegradation. We also did mass balance of the contaminants in the sludge phase. Now, in this case, the sludge comprises the biological sludge plus the activated carbon. And we found that, yes, the compounds that have high hydrophobicity, they will be absorbed onto the sludge. But if a compound is hardly biodegradable, if it does not get significantly biodegraded, then that compound can also remain in the sludge, even though it has less hydrophobicity, or it is hydrophilic. So all these results were actually pointing to the fact that we can combine different techniques, but eventually the biodegradation needs to be improved, because otherwise we will end up with sludge that has a lot of trace organic contaminant. So even though the effluent, the aqueous phase may be clear, may be devoid of such trots, the sludge phase may still contain significant amount of them. So we moved ahead with our work, and the next few slides will communicate to you our approaches to using high retention membranes with MBRs, and also to improve biodegradation by applying bioaugmentation. Now, high retention membranes, I'm sure the audience is aware of them. They can be nanofiltration, reverse osmosis, where the pore size is pretty small. However, there are other high retention membranes, such as membrane distillation or forward osmosis, which do not necessarily work by the sieving action, or do not necessarily depend on the pore size of the membrane. So I'm not going into the details of the basic principle of membrane distillation, but let's assume that it is a high retention membrane, where water can only pass through the membrane in vapor phase. Therefore, any compound that is not volatile will be retained within the reactor. Now, because we combined membrane distillation, which is a high retention membrane, with the bioreactor, the final effluent was completely free of any of the trocs that we tested. However, we found that the trocs that were retained within the bioreactor, if they were not subsequently biodegraded, their concentration will eventually increase in the supernatant. Right, so this is a limitation of the biodegradation. So yes, by membrane, we can retain all of them in the bioreactor. This may promote biodegradation of some compounds because you have longer retention time and so on. However, eventually there will be some accumulation because those compounds are not getting biodegraded even though they are retained within the bioreactor for a long time. Similar results were observed when we tried forward osmosis coupled with MBR. Now you know in forward osmosis, the treated effluent gets into a draw solution, which from where, if we want to recover clean desalinated water, then we have to couple it with the reverse osmosis. So in this case, we coupled the reverse osmosis after a conventional MBR as compared to coupling reverse osmosis after osmotic membrane bioreactor, where we used a forward osmosis membrane. The performance was similar. Again, the forward osmosis membrane would help to retain the trace organics which are not getting biodegraded, but eventually we will have build up of those chemicals which are not getting biodegraded. We also tested a few other factors when we are combining MBR and RO compared to forward osmosis MBR and RO. And we found that the RO membrane fouling may be less critical when we are combining that with forward osmosis MBR or osmotic MBR, and so on. So we, in the last few slides, we talked about combining high retention membranes with with bioreactors, therefore constituting high retention membrane bioreactor. Now, we did a literature review on the relative performance of trocs biodegradation when we use a conventional activated sludge process versus conventional MBR versus a high retention MBR. Remember, we are comparing here the degradation, not the removal. In terms of removal, from the aqueous phase, the high retention MBR would be the best because the high retention membrane is there to take away to retain all the trocs and give us trocs-free permeate. But we are, in this graph, we are talking about the extent of degradation of the compounds that are being retained within the MBR. And we found that in high retention MBR, we may achieve better biodegradation than the conventional activated sludge process. However, that may not be significantly better than that in conventional MBR. So what can we do? Can we find an option to improve the degradation of the trocs? We want to have degradation because otherwise we will produce sludge which is rich in these trocs, and then we'll have to have other ways to deal with that sludge. Excuse me. So one of the approaches that we tried is, again, to use the white rot fungal system. I don't think we have the time to discuss all the details about the mechanisms in which this fungus can degrade contaminants. But let's say that they have a combination of extracellular and intracellular enzymes, which can help us degrade compounds which will not be normally degraded by bacteria that are common in conventional wastewater treatment plants. One of those extracellular enzymes is lactase, but then there are other enzymes such as peroxidase and so on. So initially what we tried is we inoculated the whole cell fungus into a conventional bioreactor. After we inoculated, we did not control sterility. So we let other bacteria to come in and grow in the bioreactor. So eventually it was a mixed culture, even though we started with a pure culture. And in that study, we were able to show that for some compounds which are originally hardly biodegradable, we can derive benefit if we augment the bioreactor with this kind of fungi. So that was one approach. We inoculated the whole cell of the fungi. We eventually also tried to use only the enzyme. So we do not inoculate the sludge, rather we extract the enzyme from the fungus and then construct an enzymatic membrane. Now in this study, the membrane that we used is the ultrafiltration membrane. So it was just enough to retain the enzyme within the bioreactor so that we do not have to continuously dose enzyme. However, it was not small, the pore size was not small enough to retain the trophs. Okay, so we would still depend on the biodegradation by the enzyme for the trophs removal. But interestingly, what we found here is even though the membrane does not have a pore size which can retain the troughs, we did find that the concentration of the troughs was higher within the bioreactor than in the permeate. So that means that the membrane eventually is retaining some of the troughs, even though its pore size would not allow it to do. So eventually we found that the enzyme that we used were creating a layer on the membrane, therefore helping to retain some troughs. And it was beneficial because after retention, the enzyme would have more time to complete the degradation. So this study clearly showed why we should use an membrane enzymatic reactor rather than just a conventional enzymatic reactor, because the membrane can enhance the biodegradation. Right. I am aware of the fact that I'm showing a lot of data here, but I'm trying to show only the take-home messages. I'm not trying to go into the details, but hopefully you would understand, but of course I'm here to answer any questions. Now, in the previous slide, we used an ultrafiltration membrane, but it showed that some kind of enzymatic layer on the membrane can eventually lead to better degradation. So then we thought, okay, so we have an enzyme which can degrade compounds much better than conventional bacterial culture. Then how about combining the high retention membrane with this enzymatic degradation? Clearly, when we combine a high retention membrane, the permeate, the treated effluent, will be free from the troughs because the membrane itself is retaining. But again, we were interested about what would happen after the troughs are getting retained with the bioreactor. And interestingly, we found that when we use the high retention in membrane, the biodegradation by the enzyme actually was improved. It was interesting, but then we had to explain this as well, because all we have changed is the membrane. Membranes can retain. How can they improve biodegradation? We subsequently were able to explain that it is a matter of having longer retention so that the enzyme would have the time to complete biodegradation. And there are other considerations such as redox mediation and so on. I would rather not go into that part because it may become a bit complex to explain within the limited time we have. Look, I am known to go through the slides very fast, and I think I'm doing pretty well in terms of time. So I do not actually have many slides left, so I will go a bit easy from here on. Now, I talked about my connection to Japan and University of Tokyo. That connection still continues. We do have collaboration with University of Tokyo. And this shows a recent MOU signed with them. Now, while I was learning about MBR, I was approached by IWA to edit a book on MBR. And I was fortunate to edit that with my mentor, Professor Yamamoto, and Professor Chun Hak Lee, another well-renowned MBR person from Seoul National University. I consider him another mentor that I was able to have in my career. So look, I do not dream to be a millionaire by selling this book, but if it helps the researchers and the students, that would be the best thing that I can get from editing this book. So I'd like to thank our sponsors, the grant authorities that support our work. And of course, our laboratory is sustained by the hard work of the students and researchers, the current and the past members. So I would like to acknowledge their contribution and thank them wherever they are at the moment. If you don't know, I am also associated with the Membrane Society of Australasia. I'm one of the members of the board of directors. And I invite you to get associated with our society. We are doing a lot of interesting and exciting work, and your participation would be highly appreciated. That's actually all that I had. I'm sure you will have some questions to ask me. So I will conclude my presentation for now and then wait for any questions that you may have. Thank you.
Thank you, Faisal, for delivering a very interesting presentation. Now it's time for Q&A session. If you have any question, you can unmute and ask the question directly or post the question in chat.
Maybe I start first. Thanks, Faisal, for your wonderful talk. So we know actually over the last 20 or 30 years, MBR is one of the greatest success in the membrane field, from the lab, and now actually, the MBR is widely applied in the water industry. And we have so many, I think, young researcher, next generation researcher. Could you share your personal perspective on the future direction for the MBR. So what will happen in the next 5 or 10 years?
Thank you, Siwang. You are right. This has been a marvelous development by many researchers. MBR is now at the forefront of wastewater treatment and reuse. The future direction, if we look for papers on MBR, we will find many papers on membrane fouling. Its literature is replete with such papers. But Professor Yamamoto used to say one thing, let's make friendship to fouling. So fouling will be there. And we will just have to learn to live with it, like we will have to learn to live with COVID. And the suppliers, MBR suppliers, now have already proposed protocols to clean them periodically, and they are eventually improving the membrane efficiency. So I would say the next step would be, one, to test MBR's performance in terms of tackling the emerging contaminants. Not only emerging contaminants, but also disinfection, because this is very important if we want to have water reuse. And also to improve the energy consumption or reduce the energy consumption. So aerobic treatment requires aeration, and aeration consumes around 60% of the energy cost in MBRs. And in MBRs, you need aeration to clean the membranes. So membrane design to have more surface area per unit volume of the module, that would reduce the energy consumption and so on. So I think we are embarking on a stage where the research now has to target improving its applicability even further.
Thanks. Maybe one more question. Sorry for me. Our conventional MBR is, as you mentioned, we need to pump air. It's a aerobic system. I think now actually the industry, I think quite keen on anaerobic based MBR. I know actually in Singapore, they have already built, I think, a few small scale, I think, demonstration project to treat the industry wastewater. Could you actually share your thoughts or comments on this technology?
Sure. So when the anaerobic biodegradation was first introduced, there was a big uptake because it can reduce energy consumption. However, we need to also acknowledge the limitations of anaerobic degradation, because anaerobic degradation is not complete. So anaerobic degradation will not lead to carbon dioxide and water. We will have intermediates. So some aerobic polishing will be required. But I do agree that anaerobic MBRs will find more and more application in the future. So yes, the prospect of anaerobic MBR is good.
Thanks, Father. Yeah.
Thank you.
Is there any question from other audience?
Yeah, I have one question, Faida. It's a very impressive presentation. It's a great honor to hear about the bestseller author's presentation. Yeah, thank you. And I just wondering your nutrient recovery. You didn't mention about anything about the nutrient recovery. So if you could share a little bit of what's your strategy and what's the future of the nutrient recovery from the MBR effluent, that could be one question. And then second question is about your membrane distillation submerged hybrid system. So now MD itself is very much a wetting issue. So you want to put the MD inside the MBR, which will accelerate the wetting issue. So what do you? Is it like only for the publication related research, or do you believe the MD submerged MBR would be good future? What's your perspective? So if you can share two questions.
Thank you, Sean. Very good questions. In terms of nutrient recovery, we tried forward osmosis. For example, forward osmosis to recover nitrogen and phosphorus from sludge centrate. So we could recover nitrogen and phosphorus from raw wastewater as well, but the process works much better if we apply this recovery process when the sludge has been taken out of MBR and has been digested in an anaerobic digester, and the supernatant that is rich in nutrient, and then we can use forward osmosis to recover nutrient from that. So actually the challenge of nutrient recovery from wastewater is that it is very much diluted. So it has the wastewater does have nutrient, but it is diluted. So we need to have a concentration system. So one way to deal with it is to do this nutrient recovery from the sludge digestion centrate and apply forward osmosis. Now, referring to your second question, the use of membrane distillation. You have touched a very important point, the membrane durability, or the how long is the membrane going to retain? It's whether the membrane wetting problem will be more significant in MBR or not. I think at the first place, where MD could be used. An MD membrane amended process can be feasible when we have waste heat. Because of the formatting, or because of the format involved, membrane distillation can be operated by waste heat or solar-driven heat sources. Otherwise, if we need to use other form of energy, this process is not going to be feasible. So that's the background of where we think a membrane distillation could be combined with MBR. In terms of membrane integrity, you are absolutely right. And in our studies, we operated with the aim of observing the performance in terms of biodegradation. I think the next step is to work with membrane fabrication experts like you or C1 or Wanting to see how the efficiency of those membranes can be improved so that we can prevent membrane wetting when we are using it in conjunction with bioreactor.
Okay, thank you.
Thank you.
Thanks, Professor Faisal, for your nice presentation. I just have a general question. If you could please kindly go to your first slide, since I see you put a journey you had after your PhD and then maybe as a research fellow and by now. If you could kindly please go through that journey if you have a good time. I think it should be interesting for PhD student, early career researcher, your personal journey through this within these years. Thank you.
Thank you. Yes, that's the reason why I put that slide in, just to show the upcoming researchers how you can approach to an established academic career. And because I have got a bit of time, I can explain a bit. There are challenges in trying to move from one country and then get reestablished in another country. So my journey, my transition from Japan to Australia was also characterized by that challenge. I, by the way, was born and brought up in Bangladesh, so I completed my undergraduate degree in civil engineering, focusing on environmental engineering from Bangladesh University of Engineering and Technology. And then I received a scholarship to join University of Tokyo. And I went there without knowing what membrane is and without knowing who Professor Yamamoto is. So look, I was not that smart like the youngsters nowadays. At that time, my only aim was I need higher studies and I will go to a good university and work on something regarding environment. But destiny took me to University of Tokyo. And destiny took me to Professor Yamamoto's labs, and I had nothing to do with that. So I just landed there. And then the first day I met Professor Yamamoto, and he was presenting in a laboratory meeting, and he said that, look, we use membrane for physical separation. And this is very interesting because it is easy to monitor. If there is a physical separation, you can even a lay person can see that some particles are being removed. So that's the first thing that drew me into membranes. Look, okay, so I completed my PhD and then I did my postdoc and I stayed a bit longer because my wife was also doing her PhD in medicine there. So we stayed until she completed and then we said, okay, it's time to move on. Even though I could remain at Professor Yamamoto's lab forever, I think. So then I was looking for opportunities, and this opportunity at UOW came along, and then I moved in there. I shifted there, and I was very fortunate to work with some very dynamic researchers at UOW. Who helped me to develop and take the opportunity when something came along. This move from Japan to Australia, that was a calculated risk that I took, and it worked. So that's why I can speak in front of you at the moment. But it was challenging. Now that I look back, I feel that was a move that worked well, but I was actually lucky that it worked well. And again, I need to thank the environment, the colleagues, and the university that gave me such opportunity. Sorry, I took a long time on this slide, so I'll just stop there and then let others to ask any questions if they have.
Thank you.
Question. For your work with the GAC, did you observe whether there is any disintegration of the activated carbon over time, and whether there is any damage or erosion on the membrane surface?
Okay. So we used granular activated carbon as a post-treatment, but when we combined it with MBR, we used powdered activated carbon. But the points that you have mentioned are really important because some researchers have used powdered activated carbon dosing into MBR or membrane systems to prevent fouling. And then the reports available are contradictory. Some say it helps in improving fouling. Some say, oh no, actually it's going to affect the, exacerbate the fouling. In our study, we did not find any negative impact of PAC addition into MBR. But as I said, there are, I would say that it has to do with the aeration intensity that we are going to use and so on. And eventually we will need to replenish the powder activated carbon or granular activated carbon, whatever we use, because we have to withdraw some sludge. With that, some activated carbon will also be withdrawn, and then we will have to dose some fresh activated carbon, and in that way we can maintain the original size distribution.
Thank you.
Thank you.
So following up the question of Felicia's, I just wondering, so there are several biocarriers in MBL. So some people are using some plastic, some people are using sponges, some people are using activated carbon. So based on your experience for last almost 20 years, so what do you believe which kind of carrier in MBL is the best choice?
Question, Sean. Now, the difference between activated carbon and any plastic carrier, I think the main difference is activated carbon. I'm forgetting the exact word, but activated carbon has absorption capacity, whereas those plastic carriers do not have the absorption capacity. They are just carriers. So activated carbon is not only acts as a carrier, but also it can improve absorption of the bacteria and the contaminants onto the activated carbon particles, and therefore can improve the biodegradation. So from that perspective, it is same as using activated carbon versus using sand particles, because sand particles do not have absorption. So from that point of view, I would probably lean towards activated carbon. However, I think the real suitability will depend on the type of the wastewater. So I think for any real application, we need a pilot scale testing.
Okay, thanks.
We have. Sean, you have other question?
No other questions.
If not, we have one question from the audience in the chat.
Yes.
Says the MBR can be effective for removal of heavy metal contaminant in wastewater, such as arsenic, mercury. Please, can you explain?
Right. So when we talk about heavy metal removal from wastewater, we actually mean that we promote their precipitation into sludge, and then we remove the sludge. Because metals are not something that microorganisms can degrade. So heavy metal removal in any biological process or any other process will be precipitation onto sludge and then remove them. Now, because in MBR we have membrane, and on the membrane we have a sludge layer, which we call cake layer. Due to this cake layer, removal of some soluble contaminants can be much better than in activated sludge process. So that's why it is said that heavy metal can be better removed in MBR compared to conventional activated sludge process. I'm not sure whether I have answered your question, Tommy, but please do ask me if you have other questions.
Any other question? If there is no other question from the audience, I would like to thank Professor Faisal Harith. Before we end the webinar, I would like to share our upcoming event. I hope everyone can see my screen.
Yeah.
So we will have Dr. Jingguan from Origin Water, who will be presenting on the 8th of September. And Dr. Songli Xie from CSIRO will be presenting on the 6th of October. And we are also organizing IMSTEC, the International Membrane Science and Technology Conference, in December 2022 in Melbourne. Abstract submission is now open, so please visit the website for further information. Once again, thank you, Professor Hay, and thanks to our co-organizers Professor Siwang, Professor Wanting Wang, and Dr. Sunong. And thanks everyone for joining the webinar. We hope to see you again in our next event.
Thank you very much.
Thank you. Thank you.
Thank you.